One of the most important results in all of algebra is Lagrange's theorem. It's going to be absolutely essential to our understanding of the internal structure of groups, how the subgroups of a group relate to the group itself, and so forth and so on. Now, Lagrange's theorem is actually not too difficult to prove, but we do need to introduce some new notation. So we're going to introduce the notation and terminology of cosets, and then we will prove Lagrange's theorem, and we'll see a couple of applications of it. So let's start with definition 56. Definition 56 is the following. Let's let G be a group and H a subset of G. For any element A of the group, the left coset of H with representative A is the set which we denote AH. And as the notation suggests, this is the set of all products A times H, where H comes from the set big H. So at the level of sets, this is simply taking your set big H, it's got a bunch of elements in it. The left coset of H is the set that you get when you take every one of those elements and multiply them on the left by A. And we can do this for any element A of G, and we can get different sets out of it. Similarly, we can talk about the right coset. The right coset of H with representative A is denoted HA, and again, the notation just means we take all the elements of H, multiply them on the right by A. Because the group G may not be abelian, these two sets may be different, although when G is abelian, of course, these two sets are the same. That's actually going to be relevant to us in a later lecture. Now, I've stated the definition here for an arbitrary set H, but in basically every application, every case we care about, H is actually going to be a subgroup of G. That's going to be the type of subset that we care about. So when H is a subgroup of G, the number of distinct cosets of H in G is called the index of H in G, and it's denoted the following way. Absolute value bars G colon H. So this is supposed to sort of suggest this G colon H sort of a division sort of thing. We're not exactly dividing, of course, because these aren't numbers. But the idea is that if we look at all the different cosets of H, that's going to be a bunch of different subsets of your group. And the number of different subsets of the group is the index of H in G. Now, as we're going to see, these cosets that we get are all going to be disjoint from one another, and they're going to cover the whole group G. In particular, this means that the cosets of H are going to form a partition of G, a fact that we're going to take quite a bit of advantage of. And there's going to be some other facts that we're about to see that sort of explain why this index idea makes a lot of sense. But before we do that, let's see some simple examples. So let's let G be the set Z mod 6Z, which is the set 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. Let's let H be the set 0 bar, 3 bar. Now, in this case, H actually is a subgroup of G. And let's look at all of the different cosets of H. Now, when we write G additively, we can have a different notation. So additive cosets will typically look like A plus H or H plus A, rather than the A times H and H times A that we have in the multiplicative case. So we have the following cosets. We're going to look at 0 plus H, 1 plus H, 2 plus H, 3 plus H, 4 plus H, and 5 plus H. There are 6 different ways of constructing a coset, or 6 different representatives of a coset. And in order to get the coset 0 bar plus H, for instance, we're simply going to take 0 bar and add it to each of the elements in H. So 0 bar plus 0 bar is 0 bar, 0 bar plus 3 bar is 3 bar. Now we take 1 bar plus H. 1 bar plus 0 bar is 1 bar. 1 bar plus 3 bar is 4 bar. And we continue. In each case, we're simply taking our representative and adding it to each one of the elements in H. 4 bar plus H bar is 4 bar, comma, 4 bar plus 3 bar is 7 bar, which is 1 bar. 5 plus 0 is 5 bar, and 5 bar plus 3 bar is 8 bar, which would be 2 bar. So there are a few things to note about this. First of all, notice that we have some duplication. We have that 2 bar plus H is the same as 5 bar plus H. And so we have the same coset that can be represented a different way with different representatives. Similarly, the cosets with representatives 1 and 4 are the same, and the ones with 0 and 3 are the same. So that's the first thing to note. Furthermore, notice that when we do have the same representative or different representatives rather for the same coset, those representatives are exactly the elements of the coset itself. And so the 1 bar and 4 bar are the same, but that's because they're both elements of the coset consisting of 1 bar and 4 bar. Excuse me, and so forth, so on. In particular, we can also see that all of the cosets have the same size. All these cosets are of size 2. And we can see that there's no overlap between them. If you take 2 different cosets, then there's no overlap between these 3. So a whole lot of things to point out here. Let's look at another example and see if we can spot some similar patterns. Let's let G be S3. So this is the symmetric group of degree 3, the set of all permutations of 3 elements. And let's let H be the set consisting of the identity and the transposition 1, 2. Again, we have that H is a subgroup of G. And we've got, I don't want to look at all of the cosets here, but we can look at a couple of them. If we take 1, 3 times H, that's the set of permutations 1, 3 times 1, and then 1, 3 times 1, 2. And when you simplify that down, get it down into its disjoint cycle form, that's 1, 3, comma, 1, 2, 3. And if we take the right coset, that's going to be given by 1 times the cycle 1, 3, and then the cycle 1, 2 times the cycle 1, 3. So we're going to get 1, 3 again, but this time we're going to get 1, 3, 2. So a couple things to note here. First of all, note that these two are different, indicating that the left and right cosets of a subgroup can in fact be different, even with the same representative. However, they're still the same size. They both still have size 2, which is the same as the size of H to begin with. And furthermore, the representative that we took still shows up in both cosets. So we're going to bring together a lot of the observations that we've seen into a lemma, which is going to have a lot of parts to it that just talk about the various structure facts that we have about cosets that are going to be absolutely vital to much of the stuff that we do in the upcoming weeks. So let's look at lemma 57. Let's let G be a group and H a subgroup of G and A and B elements of G. So the first fact, which is going to drive the rest of much of the rest of the lemma, is that the relation twiddle defined by A twiddle B if and only if A inverse B belongs to H is an equivalence relation. And given any equivalence relation, we have equivalence classes of elements, and we know that the equivalence classes of elements form a partition. So we want to specify that the equivalence class for A is AH. So this is telling us that the cosets of a subgroup are in fact also equivalence classes under a particular equivalence relation, which we are going to take advantage of quite a lot. Now, let's see the rest of it. Many of these statements are going to follow immediately from part 1. So part 2 of lemma 5.7 says that A belongs to AH. Every element belongs to the coset it's a representative of. We have that AH equals BH if and only if A inverse B belongs to H. Part 4, AH equals BH if and only if A belongs to BH. Part 5, AH equals BH or AH intersect BH is empty. Part 6, if I take the coset of H with representative AB, that's the same as the coset of BH with representative A. So there's a sort of associativity of cosets here. Number 7, the order, or the cardinality, I should say, these aren't necessarily groups, but the cardinality of AH is the same as the cardinality of BH. And 8, if AH does in fact happen to be a subgroup of G, then A belongs to H. All right, let's talk about a few of these. Before we launch into the proof, let's look at some of these. Some of these will follow immediately from part 1. And so I'm just going to talk about those briefly here. So part 1 says that we've got this equivalence relation tilde, where A is related to B if and only if A inverse B belongs to H. So that's an equivalence relation, and the equivalence class for A is AH. Let's assume that we've proven part 1 already. Then part 2 comes from the fact that tilde is reflexive. So that means that A is related to A. So that means that A is in the equivalence class of A under the relation tilde. All right, part 3, AH equals BH if and only if A inverse B belongs to H. So this is the definition of the equivalence class. And similarly for part 4. This definition of equivalence class, this was one of our homework problems, which says that an element of an equivalence class is a representative of that equivalence class. So if two cosets are equal, then that means that each representative involved belongs to the coset. Part 5 also follows because we have that the equivalence classes form a partition, which means that if any two equivalence classes are not identical, then they have to be disjoint. So when you look at all of the equivalence classes under any equivalence relation, there's no overlap between them. Any two equivalence classes are either actually one or they have nothing in common. So items 2, 3, 4, and 5 of this lemma are all pretty immediate consequences of part 1, and we're not going to explicitly write that down. One thing to note about part 6, which we are going to have to go and talk about, but first of all, this BH expression that we get down here may not be, or it might not be, a subgroup of G. So we had the definition of cosets for arbitrary sets. We may have to use that in practice when we want to apply part 6 here, because BH might not be a subgroup. Part 7 is more important than it initially appears. It says that all of the cosets of a given subgroup are the same size. And this is something that we observed in our 2 examples, and it's hopefully not surprising, but it's also quite powerful. It says that the cosets behave in a very predictable manner. They behave in a very regular manner. So no matter what representative I take, if I take A times H, that's always going to have the same number of elements in it as B times H. All right, and then for part 8, if A times H is a subgroup of G, then A has to belong to H to begin with. In other words, the only coset of H, which is a subgroup of G, is H itself. This is not going to be too hard to show, and it's only going to come up occasionally, but it's a good thing to note. So let's look at the proof of this. As we've seen, the driving result of this lemma is part 1, showing that this relation that we define here is an equivalence relation. So let's go and see how this proof goes. So proof of lemma 57. So recall that our hypotheses are that G is a group, H is a subgroup of G, A and B belong to G. So for part 1, so we want to let twiddle be the relation where A is related to B if and only if A inverse B belongs to H. So in order to show that this is an equivalence relation, we have to show 3 things. We have to show that twiddle is reflexive, symmetric, and transitive. So let's check out reflexive. So we need to show that A is related to A. Since H is a subgroup, the identity belongs to H. So that means that A inverse A, which is the identity, belongs to H. So that means that A is related to A. All right, let's show that it's symmetric. So let's suppose A is related to B. And we want to show that B is then related to A. This means if A is related to B, that means that A inverse B belongs to H. Now, since H is a subgroup of G, H is closed under inverses. So that means that A inverse B inverse belongs to H. So A inverse B inverse is B inverse A inverse inverse belongs to H. But of course that means that B inverse A belongs to H, because A inverse inverse is just A. Therefore, well, now we can see, okay, B inverse A belongs to H. That means that B is related to A. So we've shown that twiddle is symmetric. Let's check transitivity. So let's suppose that A is related to B and B is related to C. Oh, I suppose up at the top I should say that A, B, and C belong to G. So that this means that A inverse B belongs to H and B inverse C belongs to H. Now, since H is closed under multiplication, that means that H contains A inverse B times B inverse C, but of course we've got associativity, so this is A inverse times B, B inverse C, and B and B inverse are just the identity. So we just get A inverse C. So that means A inverse C belongs to H, which means that A is related to C. So we've shown that the relation twiddle, or tilde, is reflexive, symmetric, and transitive, and therefore it is an equivalence relation. Now there is a little bit more that we have to do, but I want to take a pause here to mention that as we're going through this, as you're reviewing this, note that this relation, A inverse B belonging to H, is in fact, the order of this matters a lot. The fact that we have the inverse on the first element here is important. So I note that this is not the same as saying that A B inverse belongs to H. So you may well ask, well, what if we do define an equivalent, or try to define a relation using the condition A B inverse belongs to H instead of A inverse B belongs to H? Turns out you can still show that this is an equivalence relation. The difference will be that the equivalence classes under the red relation here, the other one, will be the right cosets of H, and we're working with the left cosets in this lemma. Excuse me. Now, while the lemma that we're working with only is talking about the left cosets, in fact, all the same results hold for the right cosets, and you would prove that using this relation right here. So this, I will say, gives the result for the right cosets HA. Excuse me. So now let's look at the equivalence class of A under this relation, and let's show that it's exactly the cosets. So let's, for the moment, let bracket A be the equivalence class of A under this relation. We want to show that the equivalence class of A is exactly equal to AH. We're trying to show an equality of two sets, so let's prove both inclusions. So if B belongs to the equivalence class of A, then A inverse B belongs to H. So that means that A inverse B equals H for some little h in big H. Now multiplying on the left by A, we get that B equals AH, which, of course, by definition, belongs to the set, the left coset of H. So that means that we've shown that the equivalence class of A is a subset of the left coset AH. So we've done half of that. I'm going to get a new page for the other half. So now, suppose that B belongs to the equivalence class of H. Therefore, B equals AH for some H in H, and then multiplying on the left by A inverse, we get that A inverse B equals H, which is, of course, an element of the subgroup H. So that means that A is related to B. Hence, B is in the equivalence class of A. So that means that AH, the coset AH, is a subset of the equivalence class of A. Therefore, the equivalence class of A equals the left coset AH. And this is the part of the argument that would be slightly different if you change the definition of the equivalence relation, and you would get the right cosets instead of the left. Okay, so we have this equivalence relation. We've shown that the cosets are in fact the equivalence classes of this equivalence relation. Therefore, they form a partition and so forth and so on. So let's move on and see the other parts of the lemma. As I said, parts 2 through 5 are all immediate from early results on equivalence relations. There isn't even anything of algebra in this. It's just the equivalence relations. You don't have to use the group properties or anything in order to get parts 2 through 5 once you've proven part 1 to show that you actually have an equivalence relation and you've identified the equivalence classes. All right, so let's look at part 6. Part 6 is just tracing out the definitions. Part 6, we want to show that AB times H is equal to A times BH, or the cosets, I should say. So by definition, AB times H is the set of all AB times H, where little h belongs to big H. By associativity, we have that this is A times B little h, where little h belongs to big H. But now, if I look at the set of all BH, where H belongs to big H, this is precisely the set of all H primes, which belong to BH. These elements right here, the B little h for H in big H, that's by definition the set of all elements in the coset BH. But now the set of all elements A, H prime, where H prime belongs to BH, is again just by definition the set of cosets of the set BH. So nothing clever to do with part 6. We're using just the definition, and I suppose we're using associativity of multiplication in the group. That's all. Okay, part 7, we want to show that all cosets have the same size. We want to show that the cardinality of AH is equal to the cardinality of BH. Now we're going to simplify this a little bit. We're going to show that every coset has the same cardinality as H itself. And so because they all have the same cardinality as H, they all have the same cardinality as each other. So let's let phi from AH to H be given by, oh, I'm sorry, I want to go the other direction, from H to AH. From H to AH be given by phi of some element H be just what you get when you take A times that. Now, whenever you're setting up a function like this, you do need to make sure that that it's well defined, meaning, among other things, that whatever element you plug into the function, you always get something out in your codomain. So no matter what element of big H I plug into my function, I should get something in AH out of it. And of course, this the way that we've set up the definition here works perfectly well that way. So phi from H to AH is given by phi of H equals AH. And what we want to try to show is that phi is a bijection. We can do this using an inverse function, but I think in this case it's actually easier just to prove it directly by proving that it's injective and surjective. So let's suppose that phi of H equals phi of H prime. This means that AH equals AH prime And by cancellation, that means that H equals H prime. So phi is injective. Now, for surjectivity is basically by definition. Phi is surjective by definition. The set AH, by definition, is the set of all A times H, where little h comes from big H. But that's precisely the set of all phi of H, where little h comes from big H, which is just another way of writing the image of phi. And remember that being surjective means that your image is equal to your codomain. So that means that phi is a bijection, and so that means that the cardinality of H as a set is equal to the cardinality of AH as a set. And because this holds for any A, that means that every coset of H has the same number of elements, namely the number of elements in H. Or the same cardinality even. H could be infinite, but in particular this shows that they have the same cardinality because there's a bijection between them. All right, finally, let's go to part 8, which said that if AH is a subgroup of G, then AH has to equal H. So note that if AH is a subgroup of G, then in particular that means that the identity has to belong to AH. Since E also belongs to H, we have that E belongs to the intersection of AH and H. Now, by part, pardon me, let me check that. By part 5, we know that the intersection of any two cosets is either the whole coset or it's empty. Because the identity belongs to the intersection here, these two cosets do not have an empty intersection, which means that we must have that they are equal. So we're using here the fact that H is itself a coset. H is the coset with representative of the identity element, as well as any other one. So this means that we could also say that this also means that A has to belong to H. So the coset of H for any element of H is just the set H back again when H is a subgroup of G. All right, so that was a big lemma. Gives us a lot of structure that we're going to use. And in fact, we've basically already done all the difficult parts of proving Lagrange's theorem. Nevertheless, Lagrange's theorem is very, very important, hence the name. So let's just get right to it. Let's get to Theorem 58, which is also called Lagrange's theorem. And it's a theorem about finite groups. If G is a finite group and and H is a subgroup of G, then the order of H divides the order of G. Furthermore, the index of h in G is equal to the quotient of the order of G and the order of H. So notice that this last statement here is just an equality of numbers. It's just numbers on both sides of the equation. This theorem winds up being very important because all of a sudden we can narrow down our sets of possible subgroups of a finite group quite dramatically. This means that if G is, say, a group of order 40, I know that there is no subgroup of order 12 inside it. And I know that because 12 does not divide 40. Similarly, there's no subgroup of order 9, there's no subgroup of order 30, because those numbers do not divide 40. So Lagrange's theorem gives us a lot of information about subgroups and groups. When we're looking at finite groups, there's a whole lot of advantage we can take of Lagrange's theorem. So let's look at a proof. And as I say, the proof is almost trivial once we have the previous lemma. So by lemma 57, the left cosets of H form a partition of G. So that means that we can we can find representatives A1, A2 up through AN in G, where N is the index of G in H, index of H in G rather, other way around, such that A1H, A2H, etc. up through ANH are the cosets of H. And so we have that the order of G is equal to the sum of the orders, or cardinalities rather, of all the various cosets. And that's because these cosets form a partition of G. Their union is all of G, but there's no overlap. So if I want to know how many things there are in G, I just add up the number of things in each one of these cosets. But by part 7 rather of lemma 57, the order of A1H is equal to the order of H for all, AIH is equal to the order of H for all I. So in fact, each one of these cosets has the same cardinality. Its cardinality is the cardinality of H, or in other words, the order of H. And so we're adding up n of those, and so we just get the order of G is equal to n times the order of H. But that's precisely what the problem was asking for. It's just rearranged. So n is the index of G, of H in G. And so if the order of G is equal to the index of H in G times the cardinality of H, or the order of H, that's the same as the equation that we were given above. So as you see, the work going into Lagrange's theorem is basically all coming from the previous lemma. We can get a lot of results very quickly about finite groups from this. Let's look at a few. Corollary 59 states that let G be a finite group, and A, an element of G. Part 1, the order of the element A divides the order of the group. Part 2, if G has prime order, then G is cyclic. And any non-identity element is a generator. So Corollary 59 Part 2 is our first step in our big goal this semester, which is to classify all finite abelian groups. Corollary 59 tells us that if a group has prime order, then we know what it is. Then it has to be a cyclic group, or we essentially know what it is. It has to be a cyclic group. And so this is the first step that is going to start moving us towards that classification of all finite abelian groups. All right, let's see the proof of this. Part 1 is pretty simple. We have by Lagrange's theorem, the order of the subgroup generated by A divides the order of G. And we also know that the order of the subgroup generated by A is the same as the order of A. And so that's it. The order of A is the order of the subgroup generated by A, and so that divides G. So any element of G has an order that has to divide the order of G. So again, if G is a group of order 40, there can never be an element of order 7 in it, because 7 does not divide 40. Part 2 is going to use part 1 immediately. So let's let A be any non-identity element of G. And let's suppose that the order of G is P, a prime number. So, since the order of A divides P, there are only two options. Either the order of A is 1 or the order of A is P. We know that the order of A is not equal to 1 since A is not the identity. So that means that the order of A is P. So that means that the order of the subgroup generated by A is P, which is the same as the order of the group. Now, we know that the subgroup generated by A is a subset of G. And we know that if we have two sets, one's a subset of the other, but they have the same cardinality, then they must in fact be equal. The subset must in fact be equal to the whole set. So therefore, the order of A equals, or I'm sorry, the subgroup generated by A, equals G. Which proves simultaneously that G is cyclic because there's a generator for it, and it proves that any non-identity element of the group will generate G because that's what we chose. That's what we let A be. So that's a very powerful result that we will exploit later. The next theorem includes a well-known theorem and named theorem as part of it. So theorem 60 says if G is a finite group, then if I take A raised to the order of the group, that's going to get me the identity. And part 2 says is called Fermat's Little Theorem. And it says that if P is a prime number, then a to the P is congruent to a mod P for any integer a. So let's see how this goes. Part 1 is very quick. Part 1 says that since the order of A divides the order of G, we can write that A to the order of G is equal to A to the order of A raised to the order of G divided by the order of A. This is all valid because the order of A divides the order of G. But A raised to the order of A is, by definition, the identity. And so we get that the identity is raised to the order of G over the order of A, but that, of course, just gives the identity. So that's all for part 1, one-line proof. Part 2, we are going to use some of the previous results. We do have to break this into 2 cases, though. So, case 1. Suppose that P already divides A. So that means that A is equal to P times B for some B. So now we want to prove that A to the P is congruent to A, which means that we want to prove that A to the P minus A is divisible by P. So A to the P minus A is equal to PB to the P minus PB, which is P to the P times B to the P minus PB, and we can factor a P out. So we get P times P to the P minus 1 times B to the P minus B. So that means that P divides A to the P minus A, so A to the P is congruent to A mod P. Now, for case 2, let me get a new page. It doesn't take a lot, but I don't want to crowd myself. So case 2, let's suppose that P does not divide A, and we want to show that A to the P is congruent to A mod P. So, if P does not divide A, then that means that A and P are relatively prime. The greatest common divisor of A and P is 1. And this is because P is a prime number. So, what that means is that A bar belongs to the set Z mod PZ cross. Remember, this is the set of all elements X bar, where the greatest common divisor of X and P is 1. And one of the things that we've shown is that this is a group under multiplication. Now, notice that since P is prime, Z mod PZ cross is, in fact, all of we could get it by listing all of the positive numbers up through P minus 1. Because P is prime, it doesn't share any common divisors with any numbers below it. So in particular, this means that the order of z mod pz cross is p minus 1. So now, by corollary 59, a bar to the p minus 1 is equal to 1 bar. And that's because p minus 1 is the order of the group z mod pz cross, 1 bar is the identity of z mod pz cross, and corollary 59 said that any element raised to the order of the group it lies in gives you the identity of that group. Now, in particular, if I take a bar raised to the p minus 1, that's the same as a to the p minus 1 bar, which means that this means that a to the p minus 1 is congruent to 1 mod p. Or in other words, that p divides a to the p minus 1 minus 1. So p divides a to the p minus 1 minus 1. Now, oh, sorry, I didn't want those in parentheses. So p divides a to the p minus 1 minus 1. Hence, this means that p divides a times a to the p minus 1 minus 1. Certainly, if I take something already divisible by p and I multiply it by something else, I'm not going to change it being divisible by p. So that means that p divides a to the p minus a. So we get that a to the p is congruent to a mod p, which is what we were looking for. So this is Fermat's little theorem. It can be used for quite a lot of things. We can obviously use it in order to raise things to powers if we're working modulo a prime number. However, one of the more interesting uses of it is proving that numbers aren't prime. So we can use Fermat's little theorem, which I'll abbreviate FLT, to show a number is not prime. Okay, so let's take a number which isn't prime. Let's consider the number 91. And let's suppose that we wanted to test to see whether it was prime. We can show that 91 is not prime by finding some integer a such that a to the 91 is not congruent to a mod 91. Now, the nice thing about this is that this is something a computer can check. We can use a computer to check all the numbers from 1 to 90, raise them to the 91st power, and determine whether those numbers are congruent to themselves mod 91. Doing this by hand is, of course, a little bit of a pain, especially with a number as large as 91, but we can go ahead and do it. Now, there's a breakdown of this process in the text that you can look at. In particular, you can see how we can use the method of repeated squaring in order to compute these numbers without actually ever having to find the 91st power of anything. So, we can show that 5 to the 91st is congruent to 47 mod 91. In particular, 5 to the 91st is not congruent to 5 mod 91, which means that 91 is not prime. If 91 were prime, then 5 to the 91st would have to be equal to 5, as well as, everything else. Anything to the 91st would have to be congruent to itself, mod 91. But it's not. And so we can use this to show that 91 is not prime. Unfortunately, this result can't by itself prove that a number is prime. You can't go and prove that anything is congruent to itself, mod some number, and conclude that therefore that number is prime. But this is a good way of showing that something is not prime. All right, the next theorem has to do with having multiple subgroups of a group interacting with each other and what sort of relationships they have to have numerically. So let's look at theorem 61. Let's let G be a group and H and K be subgroups of G. We have that the order of H times the order of K is equal to the order of HK times the order of H intersect K. So, before we go into it, first of all, I should mention that H and K, of course, have to be finite in order for this equality to really make sense. So one way of recognizing this, we're not going to take advantage of this precisely, but there is an intuition going on here that can help us to make connections and see the underlying structure intuitively. So this is similar to the fact that if I take two integers, m and n, and I multiply them together, this is equal to the least common multiple of m and n times the greatest common divisor of m and n. And that's one way of sort of seeing the structure here for what's going on. Because the set HK, which I'll remind us of what that is in just a second, is larger than either H or K. The set HK is a superset of both H and K. The set H intersect K is going to be something smaller than H or K because it lies inside both. And similarly, the least common multiple of two numbers is at least as big as them. The greatest common divisor of two numbers is no greater than them. And so we've got the same sort of connection here. So let's recall that the set HK is equal to the set of all products H times K, where little h belongs to H and little k belongs to K. So that's the only one of these sets that we may have been unfamiliar with. And so let's start looking at this equality and see how we can prove it. Okay, we're going to do things in the following way. We're going to construct a bijection between two sets. So note that the order of H times the order of K is equal to the order of H cross K, where this cross is the Cartesian product. it's the set of all pairs h and k, where little h belongs to h, little k belongs to k. And we also have, of course, that the set hk times the set h intersect k is the same as the order of the set hk crossed with the set h intersect k. And again, this is the Cartesian product, where this is a set of one element from hk and another element from h intersect k. And what we're going to do is construct a function phi that goes from h cross k to hk cross h intersect k, and show it's a bijection. All right. So we want to construct this function, and actually constructing it is going to take a little bit of work. So let's define phi. So for any h and k in h cross k, notice that little h times little k, of course, belongs to hk by definition. And so that's going to be the first entry in our output. So our function is going to look like phi of h comma k is going to be hk comma something. Now, let me check my work real quick. The difficulty here is, and the reason why we can't stop here, is that an element in hk may have several different representations. So we may have that some hk is the same as some h prime k prime. Multiplication doesn't have to be injective in any sort of way. We can get the same result from two different multiplications. So what I want to do is, for every element of hk, I want to pick a particular representation of it. I want to fix a particular representation. And in particular, that's equivalent to just picking one particular h that goes into it. So for every element x in hk, let's let, we want some notation for this, let's let sigma of x be an h such that x is equal to sigma of x times k for some k in k. So the point here is that if hk is equal to h prime k prime, then sigma of hk will equal sigma of h prime k prime. For every element of hk, we're picking out a particular element of h that could be used to build that element. So we're essentially associating to every element of HK a unique representation, even though it could have many of them. Now what we want to do is to let phi of HK equal the pair HK comma H inverse times phi of H sorry, let me get this right. We want to get phi of HK inverse times H. All right, and we claim that this phi is a bijection. So let's see how that goes. So let's take all of this stuff up to a new page and record all of the relevant info. So we have phi of H comma K is going to be equal to the pair HK comma phi of HK inverse times H, where HK is going to be equal to phi of HK times, let's say, K prime for some K prime. But the point is that phi is unique. Or sorry, not phi. That sigma of HK only depends on HK, on the element HK, and not its particular representation with this particular H and K. All right, so we claim phi is a bijection. Let's go through and see how that goes. So now let's suppose that phi of HK is equal to phi of H1 K1. Let's prove that it's injective. Let's assume that phi of HK equals phi of H1 K1. So then that means that HK comma phi of HK inverse H equals H1 K1 times phi of H1 K1 inverse H. So in order for two elements to be, H1 there, in order for two pairs to be equal, their individual components have to be equal. So that means that HK is equal to H1 K1 by looking at the first entry in the pair. But therefore, and looking at the second entry, phi of HK inverse H is equal to phi of H1 K1 inverse H1. I'm sorry, I keep saying phi, I mean sigma. Sigma is this symbol here. So now we have that since HK equals H1 K1, that means that sigma of HK equals sigma of H1 K1, because sigma only depends on the element that we plug in, not on its particular representation. But that means, of course, that its inverse is, that the inverses of these two are equal. So those two are equal, and hence, by cancellation, we have that H equals H1. By cancellation on that blue equation right there. We have the same element on the left, and therefore the two elements on the right have to be equal. So we have that H has to be equal to H1. So since hk equals h1k1 by cancellation, we have that k equals k1. So in particular, this means that h comma k is equal to h1 comma k1. So that means that phi is injective. So we have that phi is an injective function from h cross k to hk cross h intersect k. So then the question is it surjective? So now let's get ourselves another page again so as not to crowd ourselves. Once again, I'm just going to duplicate that up there. So now let's let now we need to have a good way of expressing this. Let's let x, y be in hk, comma hk cross h intersect k. Because we've got x, y here, we know that phi of x belongs to h intersect k, and y belongs to h intersect k. So we want to express y as phi of x inverse times z for some z, for some z in h, or let me write this, for some h in h. So we want to let h equal phi of x times y. Now, we know that phi of x belongs to h intersect k, and y belongs to h intersect k. So that means that these belong to, that this product belongs to h intersect k, which is, of course, a subset of h. So now we have that, we've got that our x comma y is equal to x times phi of x inverse h. And so now we want to express x as hk for some k, i.e. we want to let k be h inverse times x. Pardon me a second. So we have we can try setting k to be h inverse times x. Now we want to know that h inverse x actually belongs to k. If we did, then that means that we'd be able to define k this way, k to be h inverse x, and we'd be just about done. We'll wrap all this up here in a second. let's let x be written as phi of x times k prime. We know that's possible because that's the definition of phi of x. So we have that h inverse x is equal to h inverse times phi of x times k prime. Now we know that phi of x is equal to h times y inverse. So if we take this expression up here and solve for phi of x, we have that phi of x is equal to h times y inverse. So that means that h inverse x is equal to h inverse times hy inverse times k prime. Now h inverse times h is the identity. So we get that this is y inverse times k prime. Now we have that y inverse belongs to k because y belonged to k, and k prime, of course, belongs to k. That was part of how we constructed it, which both belongs to k. So this means that we can if we let h be phi of x, y, and h be, and k be h inverse x, we have that h belongs to h, k belongs to k, and phi of hk is equal to, by everything that we just did, we have that phi of hk is equal to x comma y. So that means that phi is surjective, which finishes the proof. So that was a little technical, but this last part in particular can show you basically the process that you go through sometimes in order to come up with the result. This theorem is surprisingly powerful in certain ways. So, for instance, we can use it to determine that there are no more than a certain number of subgroups of a given group. So, the result that we have, the result that we just proved, Theorem 61, says that the order of h times the order of k is equal to the order of hk times the order of h intersect k. So, for example, we can let G be a group of order 75, show that there is at most one group of order 25. We're actually going to see later on that G must contain at least one group of order 25. This theorem will show, or this example rather, will show that there is only one group of order 25. But for the moment, let's focus on just showing that there's at most one group of order 25. Or sorry, one subgroup of order 25 of G. So let's show that. Let's let H and K be subgroups of G with the order of h times the order of k being, the order of h and the order of k being 25. Now, by Theorem 61, this means that the order of h times the order of k is the order of hk times the order of h intersect k. So that means that 625 is equal to the order of hk times the order of h intersect k. So here's where we can use some arithmetic. So the order of hk, or rather hk is itself a subset of G. It might not be a subgroup because G might not be abelian, and the set hk is only guaranteed to be a group when G is abelian. So hk belongs to, is a subset of G. So in particular, this means that the order of hk, or the cardinality of hk, I should say, is, well, certainly no more than 75, because that's how many elements there are in G. There simply aren't any more elements to work with. Thus, this means that the order of h intersect k, which is 625 over the order of hk, has to be greater than or equal to 625 over 75. And 625 over 75 is, what, 4.25. Nope, that's wrong. Sorry, why have I lost the ability to do this? 75, 50 times 4. Okay, 8.33 repeating. So the order of h intersect k must be at least, well, 9. So that gives us some information already, but we also have that h intersect k is a subgroup of h. So that means that h intersect k must divide the order of h, which is 25. So the order of h intersect k is 1, 5, or 25. Now we just saw that the order of h intersect k had to be at least 9, and therefore it can be 1 or 5. So therefore, the order of h intersect k is equal to 25, and because h and k were both subgroups of order 25 to begin with, that must mean that h and k are the same. So we showed that if I did happen to have two subgroups that were both of order 25, then in fact they had to be the same subgroup. So in other words, G does not contain more than one subgroup of order 25. All right, last bit for today, we're going to talk about orbits and stabilizers and get a theorem which is similar to Lagrange's theorem in that it tells us about the order of a group related to various other numbers based on the structure of the group. So, definition 62. Let's let S be a set, G a group of permutations. On S, and A an element of S. A is now an element of the set S. So S is just a set. It could be anything. Very often it's just going to be a set of numbers, 1, 2, 3, blah, 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 up to n. And G is any group of permutations on S. It could be the whole set of permutations on S, the symmetric group on S, but it could also just be some subgroup of that. Now, given this, we've got two definitions. The stabilizer of A in G is, well, first of all, it's denoted stab, as the stabilizer of A in G. And intuitively, G is a set of permutations. It's a set of functions from S to S, set of bijections. Some of those functions will take A and send it somewhere else. Some of them will take A and leave it where it is. The stabilizer is the set of all the functions that leave A where it is, where A is stable under this. So the stabilizer of A is the set of all elements of G, all permutations inside G, where phi of A is equal to A. And notice that this is a subset of G. A related topic is the orbit of A under G is denoted orb G of A, and it's sort of going the other direction. It's saying, let's take A and ask, where are all the places that A gets sent? G contains a whole bunch of functions from S to S. Each one of them sends A somewhere. Let's look at where it goes. So it's the set of all phi of A where phi belongs to G. And notice that it's a subset of S. So it's going to be the set of all places where a given element goes. Now notice that, of course, these sets depend very much on what element you're looking at, what group of permutations you're working on. And let's see a couple of examples. Let G be the following set of permutations. The identity permutation, the transposition 1, 2, the cycle 3, 4, 5, the cycle 3, 5, 4, the cycle 1, or the permutation 1, 2, 3, 4, 5, and 1, 2, 3, 5, 4. It turns out this is a group. It's a subgroup, and I'm going to say it's a subgroup of S6. You'll notice that 6 doesn't actually appear in any of our permutations. That's fine. I'm thinking of this group as being a subgroup of the set of permutations on 6 elements. Given this, let's look at the orbits and stabilizers of all the elements in X6. So the stabilizer under G of 1, this is going to be the set of all elements in G that don't move the element 1, that don't send the element 1 anywhere. Well, the identity permutation never sends anything anywhere. And so in particular, we can see that the identity permutation will be in the stabilizer of everything all the time. The transposition 1, 2 sends 1 to 2, and so it does not belong to the stabilizer. The cycle 3, 4, 5 doesn't send 1 anywhere, so it's in the stabilizer. 3, 5, 4 doesn't send 1 anywhere, so it's in the stabilizer, and none of the other, and all of the other permutations in G send 1 somewhere. Let's do the same thing with 2, and it's actually going to be the same. The same permutations do not move 2. Notice that when we have things written in their cycle form, it's or especially in their disjoint cycle decomposition, it's easy to tell what's the stabilizer. The stabilizer is the set of all permutations that don't include that symbol as part of their cycle, except for the identity, of course. The stabilizer of 3 is going to be the identity permutation, and the transposition 1, 2. The stabilizer of 4 is going to be the same thing. And the stabilizer of 5 is going to be the same thing. And now the stabilizer of 6 is actually going to be all of G. It's going to be the whole set. None of the permutations in G send 6 anywhere. And so every element of G belongs to the stabilizer of 6. All right, so there are the stabilizers. Let's look at the orbits. The orbit under G of 1. Now what we want to do is look at each one of our permutations and say, where does 1 go? So the identity permutation sends 1 to 1, so 1 is in the orbit of 1. And the transposition 1, 2 sends 1 to 2. And then we've got a cycle which does nothing to 1, sends 1 back to 1, and sends 1 back to 1, and then sends 1 to 2, and then sends 1 to 2. So the only places 1 can go under these permutations is 1 or 2. And the orbit of 2, we want to see where this goes. So the identity element sends 2 to 2, and the transposition 1, 2 sends 2 back to 1, and those are the only places 2 gets to go under these permutations. Let's see where 3 goes. So under the identity permutation, 3 gets sent to 3. Under the cycle 3, 4, 5, 3 gets sent to 4. And under the cycle 3, 5, 4, 3 gets sent to 5. The orbit of 4, identity sends 4 to 4. Cycle 3, 4, 5 sends 4 to 5. Cycle 3, 5, 4 sends 4 to 3. The orbit of 5 gets sent to 5 by the identity, 3 by one of the cycles, 4 by another of the cycles, and those are the only places 5 gets to go. And the orbit of 6 is just 6. All of the permutations in G don't do anything to 6, and so 6 only gets sent to 6. It has a small orbit of just itself. Okay, few things to note here. First of all, the stabilizers and orbits of elements are never empty, and that's because G is required to be a subgroup, and therefore it is required to have at least the identity element in it, which means that the stabilizer of any element includes the identity permutation no matter what. Similarly, the orbit of any element of S has to include itself because any element gets sent to itself by the identity permutation. And so, because the identity permutation belongs to G, any element has to belong to its own orbit. So, we have this example here. One thing that we can see is that unlike when we were looking at cosets earlier, which all had the same size, the stabilizers and the orbits definitely have different sizes. We've got some stabilizers here which are of size 3, some of size 2, and one of size 6. And the orbits, we've got some of size 2, some of size 3, some of size 1. And so there isn't a constant size to either the stabilizers or the orbits. However, the eagle-eyed among you will have noticed that there is a balance here. A larger stabilizer means a smaller orbit and vice versa. This should be fairly intuitive because the stabilizer measures how much of G is keeping that element in one spot. The orbit is measuring how many different places it goes. And so the stabilizer, in one sense, is measuring how little something moves, and the orbit is measuring how much something moves. And obviously, if something moves more, then it is less stable, and if something's more stable, then it moves less. And so there's a sort of tension and balance in between here. In particular, you'll note that the size of the stabilizer and the size of the orbit are inversely proportional to one another, and their product is always 6. Now 6 also happens to be the size of the group that we started with, and this is no accident. This is the content of the Orbit-Stabilizer Theorem, another very important theorem that gives us a numerical measure of how the structure of a group can occur. So Theorem 63 is the Orbit-Stabilizer Theorem. And it says, let's let G be a finite group of permutations of a set S. For any A in S, we have that the order of G is equal to the cardinality of the stabilizer of A times the cardinality of the orbit of the orbit of A. Now remember that the orbit and the stabilizer live in different places. The stabilizer is a subset of the group. In fact, it's a subgroup, which is an exercise. The orbit of A is a subset of S. So let's see this proof. And what we're going to use is the following. By Lagrange's theorem, if I take the order of the group divided by the order of the stabilizer of A, this is the number of cosets of the stabilizer of A in G. This requires that we know that the stabilizer is a subgroup, which, as I said, is an exercise. For convenience, let's let H be the subgroup, which is the stabilizer of A, because we're going to keep referencing it over and over again. I don't want to make keep writing this stab GA. So we will construct a bijection between the set of cosets of H and the orbit of A. And this will show that there are as many cosets of H as there are elements in the orbit of A, which will prove that the order of G divided by the order of the stabilizer is the order of the orbit, which will prove our result. So let's let psi this time be the map such that psi of FH, I'm using F here as my general element of G. Actually, we can, we don't need to use F, we can use G. Such that F of GH is equal to G of A. Now, G of A, by definition, is in the orbit of A, because little g belongs to G, which means that little g is a permutation, and so permutation in the group G, and therefore, if I apply it to the element A, that gives me, by definition, something in the orbit. So now we need to show that this map psi is injective and bijective. Injective and surjective, i.e. bijective. So we're going to do that by constructing an inverse map. So we construct an inverse map phi. We're going to construct it and then prove that it actually is an inverse. So phi has to take an element of the orbit and give you a coset of h. So for any b in the orbit of A under G, let's let f sub b be in G such that fb of A is equal to b. We know that there exists some permutation in G that does this because B belongs to the orbit of A. And we're fixing a particular one here. Notice that this is similar to what we did in the proof of theorem 61, where we sort of fixed something specific. There could be lots of functions that take A to B, or lots of permutations that take A to B. We want to pick a particular one for each B. So now we want to let phi of B equal fb h. We want it to be the coset of h, which is with the representative fb. So now we claim that phi is psi inverse. So let's see how that goes. So recalling the definitions, we have phi of gh is equal to g of a for any g. We have phi of b is equal to fb h, and we have that the definition of fb is that fb of a equals b. Let's show that these two are inverses. So let's take phi of psi of gh, or let's be slightly more precise here. Let's let gh be a coset of h. So now, if I take phi psi of gh, that's going to equal phi of, now psi of gh by definition is g of a. Now, phi of g of a is f g of a times h, where f is a function, or where f g of a is a function that takes a to g of a. So for convenience of notation, let's let b be g of a. So we have that phi psi of gh equals fbh. Now, in order to show that these two are inverses of each other, we need the input and the output of this composition to be the same. So we want to know that GH and FBH are, in fact, the same element. We claim that GH equals FBH. Well, this is the same thing as saying that FB inverse of FB inverse G is in H. And remember that H is the stabilizer of A. So we have that FB inverse of G, FB inverse G of A is FB inverse of G of A, which is FB inverse of B. Now we know that the function, that the permutation FB sends A to B, which means that if I take the inverse permutation, that's going to send B to A. So that tells us that FB inverse of B is equal to A. So that means that FB inverse G does belong to H. So that tells us that GH equals FBH. So that tells us that we have one of the compositions that we need. When we take phi composed with psi, then we get we get the same coset back, even though it's written in a different way potentially. So now let's let B be in the orbit of A. We have that psi phi of B is equal to psi of FBH, which is, by construction, psi of FBH will be FB of A, and by definition, FB of A is B. So what we have then is that when we compose one way, we get the identity element back, and when we compose the other way, we get the identity element back, which means that psi phi is, or rather, that phi is the inverse of psi, so psi is a bijection. And so this tells us that the number of cosets of the stabilizer G of A is equal to the size of the orbit of A. So this is called the Orbit-Stabilizer Theorem. By Lagrange's theorem, this statement that I wrote at the end is the same as the statement at the beginning of the of Theorem 63 of the Orbit-Stabilizer Theorem. So the Orbit-Stabilizer Theorem allows us to relate the orbits and stabilizers of any fixed element of S together. This theorem winds up being very important in studying particularly the structure of non-abelian groups, because there's no abelian assumption here. So there we have the Orbit-Stabilizer Theorem and Lagrange's theorem, two of our most essential theorems for studying the numerical qualities of groups and their subgroups.